Let's continue on the long line model. So the approach of developing the long line model is to just investigate a small segment along the conductor. For that small segment, because it's small enough, we can treat that segment as either short line or medium line. And we develop the model for that segment, and then we consider that segment can be infinitesimal, so which will be treated at that x. So we'll have a second order linear differential equation to describe how the voltage can change from the receiving end to the sending end. So x equals 0, which means the receiving end. So if x equals L, that will be the sending end. So this will receiving end, this will be sending end. So there's only just single parameter on this equation, which is gamma. So gamma, by definition, is just a square root of z and y, a product of z and y. Z is the impedance per unit length, the series impedance of per unit length, and y is the shunt admittance to the ground per unit length. So we also mentioned if you want to calculate the square root of the product of two complex numbers, which can be still a complex number, so we need to first convert the complex number into the polar form. So make sure the angle stay within negative pi and positive pi. Then you can define the principal square root. Okay, so then we just solve this second order linear differential equations. Because it has two eigenvalues, so we will have two exponential function of x, and the coefficients a1 and a2 can be solved by using the boundary value. So if we plug in the boundary value at the receiving end, then because we already know the voltage and current there, so we actually can have two equations about A1, A2. Since we only have two unknowns, so we can solve those two. And then we'll have the accurate formula describing how the voltage and current can change along the distance of the line. To simplify this formula, we can introduce the hyperbolic function, the cosh and the sinh. So that will largely simplify this formula. Okay. Then we actually compare this one to our standard transformation model to transform the receiving end voltage current to the sending end voltage current by four numbers, four values, A, B, C, D, and which correspond to the coefficient in the formula we got from the previous slide. Okay, and it still meet the conditions for passive line because the determinant is still 1. Then later we try to rewrite the equation in a form which is comparable to the medium line. So Z prime and Y prime here, they have similar meanings to the capital Z and capital Y in the medium line, but prime here, which means it's different from the actual impedance, the actual admittance. So then we also proved, so Z prime can be expressed as a function of Z. So basically just a Z, which is the actual, the total impedance of the line, multiplied by a factor. And the Y prime or half Y prime can also be considered as the half Y, the half of the admittance. If you split the total admittance into two halves and one on each side, so that is actual half of the admittance. So that will be multiplied by a factor. Okay, so there's a very simple relationship between the capital Z, capital Y, and capital Z prime, capital Y prime. Okay, so this is what we concluded at the end of the Wednesday lecture. Okay, so now it seems the actual impedance Z and the equivalent impedance Z prime so the difference only just a factor. So if this factor is 1 or close to 1, which means we can treat this long line as a medium line or short line. But if that factor is very different from 1, so we have to make sure we use z prime instead of z. Okay, which is similar to the difference between y prime and y. All right, so let's discuss more about this equivalent pi model. So pi model is for a medium line or short line, but when we study long line model, we want to take the same structure of a medium line model, but we can somehow update, replace the actual impedance or actual admittance by some equivalent impedance or admittance, which are z prime and half y prime. Okay, by multiplying the actual parameter by some factor, so we can get those equivalent parameter. Then starting from there, we just treat this long line as just a regular medium line, but we just don't use the actual value. We just use the prime values. So that would be very convenient, especially when you study a large power system. There could be many short line, many medium line, and many long lines. So taking the same structure for the line model, which could be a pi model, is very convenient. You can just organize the data sheets with the impedance, the series impedance, including the real part on the resistance, the reactance, because of the inductance of the line, and also the half of the admittance, total admittance to the ground. We put the two halves on two ends. So for short line, medium line, we just take their actual impedance or admittance. But for long line, we just first need to change their actual value into the prime value. Then we just take the prime value. So starting from there, we just treat every line to be just the same. So that would be very convenient. But so let's just ask questions. So if we don't take that prime value, we just use the actual value. So how much error can be caused? Okay. So then we need to study what those two factors may look like. So we first draw the three hyperbolic function, because the first one, the impedance involved the factor, which is the sinh gamma L divided by gamma L, which is like the hyperbolic function about a certain value, which is gamma L divided by that value itself. So in this plot, the right curve is actually the hyperbolic sine function, sinh function. So you see it's not linear, it's pretty nonlinear. But if we focus on one small zone, for the S value, take maybe from 91 to 41, you see that portion of the red curve is pretty linear. Okay, it's almost like close to a linear curve. If we further zoom in near the origin, so that red line almost same as the straight line, which is similar to another function, the tangent function. Tangent function is this blue one. So it's very different from the red curve. But if we zoom in a small region near the origin, that can be very similar to a straight line. Okay, so which means those two factors can be very close to 1. If gamma L is small enough, close to 0. But we still want to compare the factors for medium line, long lines, and short line. Okay, so we draw this plot. X is from 0 to 1. So this is actually just assume the value gamma L, change the value from 0 to 1. For the sine function, which really just study this area, this small area, to see how that factor can change. For the tangent function, so because we only just study half of the gamma L, so we actually for tangent function we really just look into an even smaller region, how that curve can deviate from just the linear curve. So this plot is updated. If you are looking at the handout for this plot, So for in that plot, I just draw the z the ratio of the z to the z prime and the y to y prime. But here I just make some correction. So because we want to see the z prime, the ratio of z prime to z and y prime to y. Okay. So this is but conclusion will be same. This is the first factor. This is the second factor to correct the series impedance and shunt admittance. Okay. So you see, so they start from 1 when the gamma L is equal to 0. L is the distance of the line. So 0 means the line has 0 distance. So when it's 0, it starts from 1. But when it becomes longer, so it will deviate from 1. Okay. So if we draw two lines with 5% of error, which means if we just treat like 5%, it could be small error. For some engineering study, we're fine to accommodate 5% error. Then the 5% error lines will intersect with the red and blue curve at some point there, right? So which means, so if we the line is within this distance, the error will be limited within 5%.
So what is the error?
Error is just this factor, which means instead of taking a z prime, you can just take z. If you treat, simply just assume z. Okay, so this is, if you take z prime and y prime, that give you accurate result, same as the long line. We utilize, we start from a segment to develop the accurate formula to calculate the voltage current. But the question is, if we don't want to ignore this one, okay, we just treat this one as 1, treat that one as 1. So we just take the actual z and the actual y to model line. We just model the long line as a medium line. So how much error will be introduced? Yeah, so that's reflected by those two curves. Okay.
So the medium line is what I do.
The medium line means we don't calculate z prime. We don't use this formula. We just directly take z and y as the actual value, which is lambda model. We just push all the inductance, the capacitance to just into the same block. We use just lambda model. Just treat the series impedance as just single impedance. It can be in the middle of the line. And the capacitance will be split into half as two lumped capacitors on both ends of the line. How much error that can introduce? Okay. Is there any question? All right. So 5% error means if the line is not long enough, we should be able to treat it as just a lumped parameter model, like a medium line or short line. So what is the longest distance in this plot? So here the end is 1. Because the x means gamma L, the absolute value of gamma L. Gamma is, if we ignore the loss, the gamma L will be roughly beta L. Beta is the imaginary part of a gamma. Okay. So from the previous slides, beta L is actually can be calculated by this formula is the frequency multiplied by the square root of the L times C, then multiplied by distance. So for the overhead line, operating in 60 Hertz, so beta is typically 0.0013. The unit is the 1 per kilometer. Okay, which means the beta multiplied by distance will give you a value without unit. So when beta L is equal to 1, which means L is 800 kilometer. So this plot just show if the line increase the distance, the length from 0 to about 800 kilometer. So how those two factors can deviate from 1, how error can grow. So total line is 800 kilometer. So we said, so if we make a 5% error as some limit, so if we draw So which will be roughly here, right? It will be slightly, it will be half of the 800 kilometer. So which means within 400 kilometer, if the line is shorter than 400 kilometer, the error will be limited to just 5%. And if you treat this line as medium line, not as long line, okay. But definitely, if you take the long line model, that would be 100% accurate. Let's just take a look at the boundaries value we talk about separating the short line, medium lines, and long lines, right? So close to 0, that would be short line. Close to 400 kilometer, that would be long line. So we have 80 kilometer at the first boundary between the short and medium line. Okay, and the next one we have about 250 kilometer separating us the medium line, the long line. So from here we can see whether those boundaries really make sense. So if we study a short line and the error here by using the lumped parameter is very small. It's less than 1%. Probably roughly just maybe changing from 0.99 to 1.01. At the boundary of a medium line. So that error is about the 2%, maybe 2 to 3%. It's still okay. All right. So which means even if we study a line at about 250 kilometer, so that is the boundary between the medium line and the long line, and you can either choose using this accurate formula to convert Z, Y, and Y to Z prime and Y prime, then do the calculation. Or you don't do it at all. You just directly use Z and Y for your calculation. Just treat it as a medium line. So error is about 2%. Okay. And if it's shorter than this one, so the error can be even smaller. But beyond this distance, beyond 250 kilometer, the error will be bigger. It will be close to 5% or even bigger. Okay, so that's why we need to, for long line model, to make sure the calculation to be accurate. So we'll first need to convert the Z to Z prime and Y to Y prime.
Sorry, just like for how can you differentiate like the short, medium, long? Like it seems like your corresponding actuator there for 0.1, 0.2, and 0.5.
One X, the 1 means 800 kilometer. Okay, so 0.1 means 80 kilometer, right? 0.3 is about 250 kilometer, right? Yeah. So ideally, you just for O-line model, if you want to have very accurate calculation, you just always use this model. Always use long line model for every line. It's completely good, right? No issue at all. This example just tell you the difference between long line and short line model is just you need to correct the actual impedance and admittance by factor. That factor can be very close to 1. Within 250 kilometer, that factor is less than about 2%. Within 80 kilometer, that is less than 1%. Okay, if 2% is already good enough for you, so you can use the medium line. So the conclusion we have is, so a power line with both factors close to 1 can be modeled using lumped R, L, and C. Okay, how close is good? That depends on the error tolerance you want to have, you want to meet. So if 1% is okay, so you can decide within which distance you can just use the lumped parameters for the line. There's one example which is not in the textbook, but which will be a good example to demonstrate how to utilize what we learned on the long line to do some calculation. So assume we have a 225 miles 60 Hertz line operated at 130 kV voltage. which is a 3-phase power line. And here we take distributed parameters. The resistance per mile is 0.169 ohm. Inductance per mile is 2.093 millihenry, and capacitance per mile is 0.01427 mu f. And we ignore the conductance to the ground, which basically means the shunt branch, the 2 shunt branches don't have any real power. It's purely imaginary power. The line is delivering 40 megawatt power, real power at 132 kV. So this is the voltage, line-to-line voltage of the receiving end. And the power factor is 0.95 lagging power factor, which means the load current is lagging the load voltage. We want to find the sending end voltage, Vs, and current Is, line efficiency, and voltage regulation. All right, so first, we make calculate the impedance per unit length, which will be has real part R, imaginary part will be the J omega L. Okay, omega is just 377 for 60 hertz. Then you do the calculation, you have either the real and the imaginary parts, or you just have this polar form with the magnitude and angle. Okay, the unit of Z is ohm per mile per unit length. And the Y is the, it has real part G and the imaginary part J omega C, because real part is 0, so it doesn't have a G. So only it become just purely imaginary number. So the unit is, so that's why the angle is 90 degree, and the unit is mole per mile. It's just 1 over ohm. Okay, so keep in mind in the following, when we calculate the gamma, we need to utilize this definition, the principal square root. First, we calculate the ZC. ZC is defined to be, is called third impedance, is defined to be square root of the division of Z by Y. So you just direct to calculate division, it's easier just to calculate the first using the polar form. So you first calculate division of the absolute value and then calculate the subtraction of 2 angles. Okay. So when you calculate square root, make sure this part is positive and this angle is within negative pi and positive pi. Okay. So square root is simply just calculate the square root of the first number and the half of the angle. So from this result, you tell the angle is very small. It's just -6 degree, which means ZC for this case is just a roughly real number. It's very close to a real number. Next one to calculate gamma L. Gamma L is just the gamma is defined to be the square root of Z times Y, and L is the distance 225 miles. So when you calculate this square root, also make sure this one can change to the complex number of the polar form in the principal square root form. So with angle between -180 and +180. So then you calculate just the square root. So this value has angle very close to 90 degrees. So gamma L is roughly an imaginary number. So when we ignore the loss of the line, we ignore if R is 0, J also 0. So this one will be exactly real. This one will be exactly imaginary. Okay, so move on. So gamma is actually will be gamma L divided by L. So which is actually we can directly just take a real and imaginary part here. So real part is we call it alpha, and imaginary part we call it beta. So beta value here you see is actually 0.00129, right, per kilometer. So we explain, so for overhead line operating in 60 Hertz, so beta value typically around 0.0013. So how close? Very close. Later I will explain why it's very always around this value. Okay, so next we can calculate three hyperbolic function. You can use the definition of hyperbolic function, right? Using the exponential function definition. You can just use those two formula to calculate the Cauchy function and sinh function. Then use another formula to calculate this the tangent function. So for half of the gamma L. So come back to this problem. So you can get the value of the first two hyperbolic function, and the third one can be utilize can utilize that formula to calculate the third one. So next week when you do the midterm exam, make sure your calculator can translate between the for the complex number into the polar form. So those two factors, the first is z prime to z. The ratio of z prime to z is 0.964, which means if we use z, the actual z for the calculation, so the error is about 3 to 4% for impedance. And for admittance, that ratio is even closer to 1. So it's 1.018. So it only introduce about 2% error. If you believe those two factors have been very close to 1 to you, so you're fine to use the medium line model. So without calculating the prime values. Okay, so next, so we want to calculate the phasors for voltage and current on the sending end, and we can use receiving end voltage as the reference. So we already know the line-to-line voltage, and divided by root of 3 will give you the line to neutral voltage. And we just treat this one has just zero angle. We just use this voltage as the reference. So power for each phase will be the total three-phase power divided by 3. That's 13.33 megawatt. Okay, so in the calculation here, because we are going to calculate the efficiency and voltage regulation, so it doesn't matter you calculate for the entire 3 phases or just pick one phase. So here we just change the voltage, current, and power into just the values for each phase. Okay, because the IT power is actually equal to the parent power multiplied by power factor, and for the power factor, we know the angle is we know the power factor is 0.95, so we can solve the angle to be around 18 degree. Okay, so which means the current will be lagging the voltage, the reference by 18 degree. And from the power and voltage, we can calculate the magnitude of current. So next one, to calculate the voltage on the sending end, we go back to the accurate formula. We know the A1, A2 have been solved here. So you can plug in the values of IR, VR, and ZC. So we will get A1, A2 as two coefficients. Each one has unit of kV. We'll come back to this formula later, maybe next week, when we talk about some wave propagation along the line. But now we can utilize this formula. You just plug in, you just let S equals L. So that will give you the Vs and Is. Okay. So you can also directly utilize those two formulas, and so they can tell you the voltage on the sending end will be 89.3 kV with certain angle, and this is current. Okay, to calculate the efficiency, so the numerator will be just the load power, and denominator will be the real part of the compressed power from the sending end. You just utilize the definition of compressed power, which is VS times S conjugated. Then you take the real part. So the efficiency is 92%. So there's a 8% energy loss. And voltage regulation. The voltage regulation by definition is just source voltage minus the low voltage divided by low voltage. So the regulation is 17%. So it's not zero. So which means there will be some voltage drop along the line. Okay, so this is the example. Okay, so if we move on. So let's talk about a special case of the long line, which is a lossless line, the line without any loss. So we start from this accurate formula for any line, general line. So we know that the ZC is defined to be the square root of the division of lowercase z and y, and the gamma is defined to be the square root of their product. Okay, so when the line has no loss, both R and G will be 0. So ZC will become the square root of L divided by C. So the unit for ZC is ohm. And the gamma simply just become a J beta. Beta is the value is around 0.0013, right? But from this formula, the beta is equal to omega times square root of the product of L and C. So ZC is a real number, and beta gamma become a purely imaginary number. So this one can largely simplify the original two equation on the voltage and current. So let's plug in ZC and gamma. Okay. So you see, for the gamma x, the cos gamma s will be replaced by J beta x. Okay. And if we go back to the definition, so the original exponent, which is gamma x, right now become one become a J beta x, the other is negative J beta x. So you actually can, from this formula, you can recognize this is the definition of a cosine function. So this one simply become cosine beta x. So cos gamma x become cosine beta x. So for the sinh gamma x, you replace gamma x by J beta x. So this is also similar to the definition of a sine function. The difference is only just one unit of imaginary number, is a J. So this one is actually equal to J times sine beta x. So which means in the original formula, any cos function, you just change it to cosine function. Any sin function, you just change it to J times sine function. Okay, originally it's about gamma s, but now it becomes just beta x. So you can also simplify that factor. Originally, that's a sinh function of gamma L divided by gamma L. But right now, it basically just become ZC times sine beta L. And the second one will become this one. So ZC is actually the equivalent impedance along the line. because we ignore the loss, so that Z prime will become just purely imaginary value. Okay, that impedance is equal to a factor which is sine beta L multiplying the third impedance. And half Y prime is equivalent half of the admittance. So right now become this one. So if you treat this one as admittance, so this value will be equal to omega C, right? Half of omega C. All right, so immediately we can have those two formulas describing the voltage current changing with the distance on the power line without any loss. So you see here we have changed all the hyperbolic function to the sine or cosine function. And if we compare this one to the transformation with the matrix A, B, C, and D, we can match by letting the X be L. So we can match A, B, C, and D. And in this case, because we still take we take the pi model, not gamma model. So we split the admittance into half on both ends to make the model be symmetric. So we will have this relationship: A is equal to D. If the model is not symmetric, A is not necessarily equal to D. All right, so we use this model to study two types of contingencies. The first one is a short circuit at the receiving end. So when we add a short circuit, so we do some, we have fault to make the short circuit on the receiving end. So the voltage on the receiving end will become 0. And the current can be huge, right? Which is the fault current to the ground. So by using this formula, we just make, so this one will be 0. So this item will be gone. So the current from the source will be equal to cosine beta times the fault current. So because this fault current can be very high, so the source current will be the high fault current multiplied by this factor. So if this factor is small, the impact to the source can be small, but otherwise the source will be largely impacted. Another fault will be open circuit. So if we open the circuit, we'll make the load current be 0. Okay, that seems fine, right? Because it doesn't introduce high current to the system. But the impact will be on the load side because we want to know how much this voltage can change. We want to maintain this voltage within the operating region, such as maybe 5% around the nominal value. Then also from the second formula, we know. So now this item will be gone. Oh, which one? Oh, sorry. Yeah. This item will be gone. Okay. So by using this equation, we can know the load voltage is equal to source voltage divided by the factor, which is equal to cosine beta L. That same factor for the first contingency. So if this factor is close to 1, so for this case, we hope this factor can be close to 1. If this one close to 1, which means the VR will be roughly Vs, will still stay within the limit. But if this factor is very small, okay, so the load voltage can be outside of the operating region. So for the first contingency, we expect the factor to be really small, such as even you have short circuit on the low, the source is not impacted. But for the second contingency, we hope this factor to be large, close to 1. So such that the load voltage can maintain at the same voltage as the source voltage. So let's try a different value. Let's just take this value, beta equals 0.0013. Okay, let's first consider the 80 kilometer short line, which is the boundary between the short line and medium line. So 80 multiplied by this value, then that give you the radian. Then you convert to the degree. So that is 6 degree. The beta L is equal to 6 degree. So if you calculate the cosine 6 degree, that's very close to 1. So the current on the source is 0.995 IR. Okay, it's almost same as the low current. So for the short circuit fault, if that current is very high, the same current will happen on the source. Okay, so which means if you operate the system with a short line, on the low side, if you have any short circuit, you need to trip the line. You disconnect the line. Otherwise, the current will impact your generator or your source, other device. So this one can be very high. How about open circuit? For open circuit, we explained for open circuit, we expect this factor to be close to 1. Okay, because cosine 6 degrees is very close to 1. So how close? It's 1.005. So voltage doesn't increase. It's increased a little bit, but increase very small, only maybe 0.5%. So it's not big deal at all. Okay, so if you operate a short line, it's fine to open the circuit on the low. If you want to do any maintenance, it doesn't cause any impact to the generator or the source at all. But definitely, if you have a generator powering some load, if you open the circuit, you also need to reschedule the generation of the generator to keep the power balance. So how about the long line? Let's take just 400 kilometer. 400 times 0.0013. I also change that angle to be in degree. That's 30 degree. Okay, 30 degree. For short circuit fault, the source current will be about 86 to 87% of the low current. It's still very high. So if the fault current is very high, this value is still very high. So conclusion is, if you have a short circuit, you need to do protection right away. Okay, don't let the fault to impact any generator, any expensive equipment. For open circuit fault, so that the voltage will increase to 1.15, will be 15% higher than the nominal voltage. So this one is already much higher than any reliability limit. So for the transmission line, usually we want to maintain the voltage within 5%. So which means if I have a 500 kV line and you want to maintain the voltage maybe from 5% times 500 will be 25 kV. So you want to operate at 475 to 525 kV within 5%. But if you go to 15%, so that's like a 75 kV difference compared to the nominal value. So which means when you open the circuit for long line, that can be a big problem. This can be a really big concern. So later in this session, we'll discuss what actions we can take to limit such high voltage. So one method is called a shunt reactor. Shunt reactor is just like an additional inductance to the ground, which can be switched in and switched out. So when you operate a long line and the receiving end open the circuit, you want to switch in that shunt reactor. The shunt reactor will consume reactive power, and which can decrease the voltage to stay within the range. We'll talk more about that. Okay, so next we want to discuss about the load, some typical load which we can expect to give us a perfect operating condition. So that load is called a surge impedance load. Because we already defined ZC as surge impedance. So which means this load is related to that impedance. So surge impedance load is simply defined as load with load impedance equal to surge impedance. Because surge impedance itself is complex number, but if we ignore the loss, we can use this formula to calculate. Okay, originally surge impedance defined to be the load Z divided by Y, right? Because if we ignore the loss, and so we can have this simpler formula. It simply can be defined as the square root of L by C. Both L and C are a positive number. Okay, so which means ZC is also a positive number, real positive number. So if you make load impedance, you make this load impedance to be exactly ZC. So that load will be called surge impedance load. Okay, so there will be a complex power here. That load will be called surge impedance load. But usually when we talk about load, we mean the active power, not reactive power. So this means we can calculate the current, which will be the low voltage divided by surge impedance. So what is surge impedance load? So we calculate the complex power for 3 phases. So we use this formula. We know the voltage and we know the impedance, and multiply by 3. And here we want to change the line to neutral voltage to line-to-line voltage by dividing the voltage by root of 3. And because there's there's O and 2, so finally this one will be cancelled with this 3. So finally, surge impedance load is defined to be the line-to-line voltage square divided by the surge impedance, and the unit will be a megawatt. So if we, for voltage, we take a kilovolt at the unit. If we let the receiving end voltage at the reference, so with 0 angle, and the current will also have 0 angle, because the load is real, the power factor is 1. So current and voltage are in exactly same phase. Okay, so we go back to those 2 equations to calculate the voltage and current at any distance. We can plug in this equation to replace the current. So basically, we just replace IR by VR divided by ZC. Then we do some simplification. For the first one, we replace, let's make it clear. For first one, we replace by VR divided by ZC. So you see, this ZC will be canceled with that ZC. In the second equation, we replace this VR by IR times ZC. So this ZC will be canceled with that ZC. So finally, we have 2 equations. The first equation only depends on VR. The second equation only depends on IR. So which means the voltage along distance is only depend on the VR, the receiving end voltage, and the distance x. And the current only depend on the load current and also distance x. And the factor in the parentheses I colored in blue, you can recognize that one is just a unit complex number, okay, with angle of beta x. So finally, the voltage anywhere along the line will have the same magnitude. The difference is only the angle, okay? By changing x, only the voltage phase angle can vary, but magnitude will be exactly the same. Current along the entire line will be exactly the same. So that means if I have the third impedance load on the receiving end, voltage along the line is perfectly same. They have the exactly same magnitude. The current will have exactly same magnitude. And everywhere at any point of the line, if you measure the voltage and current, they're completely in the same phase. Okay, that's perfect, right? That's perfect for any operator to operate such line. That's the easiest thing. You don't never worry about where you can compensate reactive power. So perfectly, it's perfect operating condition. So which means for this case, the both sending and complex power reactive power is and the receiving end reactive power are 0. Okay, so the reactive loss of the line is completely compensated by the capacitance itself. So the line has inductance which consume reactive power, and they also have shunt capacitance which provide reactive power. So the two amounts are completely equal. Okay, so anywhere you consume the reactive power by the line will be completely provided by the capacitance of the line. Okay, that's why the voltage can be evenly can be exactly same along the line. So which means the third impedance load is very useful measure, even it will never happen. A 0 chance to happen, but it can be utilized as a measure to measure whether you need the line to have actual reactive source or actual reactive load. Okay, so if actual load is much higher than third impedance load, which means you need to add a shunt capacitor to provide reactive power. If your load is much less than third impedance load, you need to add a shunt reactor to consume the actual reactive power. Otherwise, there will be an over voltage issue. Okay. Yeah, let's stop here. Let's continue on Monday.